Every time there is a connection between two things, if it becomes a good standard, it leads to a whole ecosystem.
The world is moving toward blocks, and supply chains and trade relationships are really being disrupted.
From Orion X in association with Inside HPC, this is the At HPC podcast. Join Shaheen Khan and Doug Black as they discuss supercomputing technologies and the applications, markets, and policies that shape them. Thank you for being with us.
Hey, Shaheen, good to be with you again.
Good to catch up again, Doug. What's new?
A couple of big topics to go through pretty quickly today. One is about CXL, Compute Express Link. There's some developments there. And also our old favorite topic, chips, the CHIPS Act, and developments on the geopolitical stage in that area as well. So why don't we start with CXL? And, it's funny, I was commenting to you earlier, I kind of had the impression that CXL was already functional and operational. But in fact, the first version 1.1, is soon to be delivered, but it has not been delivered yet.
Two great topics, so look forward to talking about it. And I think the standards for CXL are still developing, at least the nice ones, the more sophisticated ones that people are waiting for. But it has been available in some fashion for some years now, except that the products that are using them have not been so plentiful, but they will be now that momentum is gathering.
Exactly. So reading a story in the Register that CXL will make its debut alongside Intel's upcoming Sapphire Rapids and AMD's Genoa processors.
Right on. So let me see if I can set the scene the way I see it.
Yeah.
Is that every time there is a connection between two things, if it becomes a good standard, it leads to a whole ecosystem. You can start at the bottom with Ethernet. And Ethernet, of course, is the vast majority of networking out there. But Ethernet wasn't fast enough. The protocol was pretty heavy. Some advances have been made. Some very recent advances have been made that make Ethernet pretty interesting. And given that there's a long lead time for some of the more high performance interconnects, the new Ethernets are becoming more interesting. But then the industry wanted something faster. So we went after things like Hippie in the old days. And then that led to NGIO, and that led to InfiniBand with Mellanox and Cornelis. People like HPE do Slingshot. People like Rockport are doing new novel implementations. Then you go one layer higher and you get to PCIe. And this was initially just an I/O bus, but then over time, especially with PCIe 4.0 and now with 5.0, it has more capabilities. It's easier to work with. In the early days, it was a pain in the neck for engineers to really work with PCIe. So now you see folks like Liquid Computing or GigaIO having switches based on PCIe. And it was very fast, but it didn't have coherent shared memory. Coherent shared memory thread started in the old days with technologies like scalable coherent interconnect. And then the NUMA systems from Sequent, and then with SGI with NUMA-Link, those were interconnects that had address coherent capability. So what if you could put that coherence protocol on top of PCIe? And that would have made it fast and coherent. And I think that's what led to a whole collection of these technologies, with CXL being the one that seems to be winning out. It was CXL, Gen Z, C6. Gen Z has now been part of CXL. And then you had CAPI and then OpenCAPI, and that too has now become part of CXL, giving it a lot of industry momentum. CXL originally came out of Intel.
So can we say that OpenCAPI and Gen Z have been subsumed by CXL?
I believe that would be a valid way of describing, given the news that we have seen. And the news was that the technology and the assets have been transferred to CXL. And C6 hasn't done, but then all the players that were supporting C6 have become part of the CXL consortium. So the handwriting is on the wall that CXL really is the winning standard here.
And that's, at least theoretically, not knowing how these various interconnects all stack up against each other technically. But it's good that there's this coalescing around one. Otherwise, you'd have several standards.
Yeah, definitely. I think it's always a trade-off between variety and trying new technologies and optimizing different things, and also having enough heft to really make a dent in the market. And maybe the experimentation phase was concluded now, with everybody kind of lining up behind CXL, is a really good thing. However, that also means that CXL now needs to rationalize the product roadmaps, make sure that all these new technologies that it now has are coherently represented in the future. And then CXL had CXL IO, CXL cache, CXL memory for different kinds of use cases. And really, the interesting one is memory, when you have a coherent shared memory across the whole thing. And that's when you can disaggregate and recompose and all that, the other stuff. And that's really hard to do. Now, there was a company called Three Leaf Systems about 10 years ago or so that had semiconductor that would also provide coherency at a distance. And the language that was used there was to pool, share, and flex. So you want to pool the resources, you want to be able to share them, and then you want to be able to flex them. And that flexing is sort of what happens at runtime. So there's a notion of, do you compose and recompose at boot time or at runtime? If you do boot time, then that's easier. If you do it while the system is running, that's a lot more difficult. To grab a piece of memory from a running system and assign it to a different running system, that's kind of harder to do. But even without that, that protocol needs to exist. And I think that the juicy stuff with CXL aren't really out yet. So my view is that we're probably going to be another 2-3 years before we see the kind of interesting stuff that is promising for CXL to show up. Now, the final frontier there is the CPU bus, the CPU interconnects. In the Intel world, we had the front side bus in the old days, and then that led to QPI, quick path interface, and then that led to ultrapath interface, UPI. On the AMD side, there was never sort of a notion of a bus. It was more like a fabric interconnect with hypertransport, and now sort of infinity fabric. And that also, hypertransport also had cache coherency capabilities. So all of these interconnects at every layer basically spawn a whole ecosystem. And I expect CXL to do that on top of what we see with PCIe.
Yeah, and they just released the specs for 3.0, even as 1.1 is about to be realized. It's sort of this Darwinian process. That's kind of the image that came to mind for me as you explained this whole process of what we've been through. But, the great potential is that CXL could be really critical for enabling these heterogeneous, increasingly composable, and more memory-centric systems of the future. So let's hope it happens.
Right on, right. And I think the architectural impact of CXL could be very interesting across the data center or within a rack at a minimum, but maybe even across multiple racks. And I see papers being written and presentations being made about the promise of what CXL can enable. All of that looks very, very interesting. And 3.0 really is the first one that is seriously interesting. And then beyond, it'll just get better.
Yeah, better and better. So now looking at developments in the chips industry, it occurred to me as this hundreds of billions of dollars in the Chips and Science Act, which includes $52 billion for U.S. domestic production of semiconductors, manufacturing. Whoever first had the insight that chips are increasingly matters of geopolitical significance for national security and economic competitiveness, and this developing notion of indigenous technology was very astute as we move increasingly, as the world increasingly coalesces into sort of these new Cold War blocs, pitting China, Russia, Iran against sort of the Western democracies and Japan, and then with other countries like India kind of playing in the middle. But the world is moving toward blocks, and supply chains and trade relationships are really being disrupted.
I think we are definitely in that phase. And even within a bloc, there are considerations for more domestic independence or more regional independence. The EU has great ambitions to put a big dent in this. Obviously, the US needs to establish or reestablish leadership within the country. And we see the work with having TSMC build systems in Arizona. And then the CHIPS Act, as you mentioned, $52 billion for the semiconductor industry, but also $81 billion for the NSF, National Science Foundation, that goes towards a bunch of these advanced technologies. It's called kind of the Chips and Science Act. And then DOE gets 40 billion. I was, catching up with these numbers. Department of Commerce gets 11 billion, and the National Institute of Science and Technology gets $9 billion. And I'm sure some of that is going to go maybe to post-quantum cryptography and all the other work that these agencies are doing, but it's highly necessary. I mean, I hear some people saying that, well, why is Intel getting so much, or why is, Global Foundries getting that much? And I think you have to remember that this activity is now a matter of national security. And especially when you think about Intel, you have to think of Intel as a semiconductor manufacturing company, not just provider of chips. And if you think of it that way, then really between Intel and then secondarily Global Foundries, those are the two big horses that we can bet on in this country.
Yeah. Yeah. Otherwise, we're increasingly reliant on TSMC in Taiwan and Samsung in South Korea, both of which have very distinct threatening enemies on their borders. And we saw this week very aggressive military exercises conducted by the PRC around Taiwan. So,
Exactly. And presumably that already caused a few days of delays for shipments. And that was just an exercise. Imagine if it becomes a little bit more serious. So, if you want reliable supply for something as important as high end chips, you need alternative geographic options.
well, yeah. And as you say, it's a matter of national interest. And given that, I have been surprised by the degree of complaint, criticism of this bill that Washington is picking favorites and its corporate welfare. Really don't agree with that outlook at all in this case.
I think there are higher priorities in play. If we need to support that capability, and if that capability manifests itself in the form of one or two or three companies, then so be it. Now, the ceremony that they had at the White House to celebrate this a few days ago had literally tens of heads of technology corporations in there. So it wasn't just sort of Intel, it wasn't just Micron or AMD, or there were a whole lot of them there in various parts of the whole ecosystem. And it's a large ecosystem. You look at the supply chain for chip manufacturing. We've talked about ASML, of course, because they have the extreme ultraviolet monopoly right now, but there's also software, there's lenses, there is simulation, there is physical layer, there is on and on and on, all of which are going to benefit from this.
Yes, exactly. Now, in the chips area, the Wall Street Journal has written two, I would say, major features around various issues related to chips. First one was a July 28th piece, I thought very good, on the race to miniaturization and this whole endless marketing and product categorization around nanometer. And but the various chip makers don't agree at all on a standard. They use this nanometer term quite loosely, and it's increasingly kind of coming into question and losing credibility.
Yeah, so the metric that I look at is number of transistors per square, whatever, right? And if you look at the transistor density, that I think is a pretty indicative number, regardless of whether it's this nanometer or that nanometer. But then as you go to 3D packaging within the chip, even that becomes a little bit, complicated. So the designations for these chip generations has been losing its meaning. So when you say 10 nanometer process, it may or may not actually be 10 nanometers.
Right,
and,
right.
And when you say 7 nanometer, it may not be. Now, traditionally, like Intel's 10 nanometer was closer to TSMC's 7 nanometer than not. It wasn't like 3 off, it was less than 3 off. And now, of course, they're not even using nanometer, they're going to 18A and 20A, and that presumably is angstroms as you go even lower than 3 nanometers. So that is another sort of a branding, but you have to really double click on it to find out exactly what that process is.
Shane, for me, being around the industry, I kept hearing nanometer and process thrown around. It finally occurred to me, I'm not sure what they're talking about. Do you know what this whole nanometer thing is actually pointing to?
Well, it's supposed to be the feature size, that this is just the width of the paths that we are etching on silicon.
Yeah, it's a billionth of a meter, a nanometer, and it refers to the length of a key component of the transistor called a gate that regulates the flow of electricity. So there you go. Well, Shaheen, what do you think of the idea of a new system replacing nanometer numbers, with other measurements? And it's kind of interesting, almost philosophically, how a designation like this is so tenacious within an industry, even as it's widely recognized to have major limitations.
Well, I think the user relevant metric is always performance and power consumption and things like that. And nanometer is a proxy for those that may or may not even pan out. So in its absence, I would vote for transistor density, how many transistor per square inch or per square millimeter or whatnot.
Now, can you get those numbers? Say
You
from
you can
from okay.
absolutely, yeah, you can, and
Oh,
you can say
awesome.
that, hey, TSMC 5 nanometer as manifested at, in the Apple M1 chip, how many transistors square inch do I have? And you get those when the chips are announced, because they always tell you how many transistors there are and what the size of the chip is.
Does it roughly correlate to nanometer?
It roughly correlates with the designation, but not exactly. Yeah.
All right. The journal did another piece about the headline being the microchip era is giving way to the megachip age. That microchips, the analogy they draw is if they were cities, the new industry wide strategy for making them better could be summed up in one word: sprawl. And I think, Shaheen, you've used sort of a city, village, town, castle analogy as well.
I have. I think that we do share the city part of it. My analogy is that chips used to be castles, and then they became condominiums, and then they became hotels, as you kind of replicated some things and did not replicate other things because they could just as well be shared. And that nowadays they're entire cities, that the whole thing is on a chip. And then with chiplets or tiles, you're going to see that more and more. And then, of course, people like Intel are talking about composability even within one physical chip. But then what is really that one physical chip when it's got half a dozen micro tiles or, chiplets on it? Well, yeah, that's kind of what he's saying, is that that's a sprawl where look at the Apple M1 chip, but basically everything is on that one chip. And it's obviously because everything is on the same chip, it's faster to interconnect. You can architecturally optimize things the way you couldn't do. So that transistor budget this time, not density, but how many transistors do I have to play with? Suddenly you can pull all manner of things on chip that in the previous generations you'd have to go off chip. So now you never have to leave town. Everything is right there.
Yeah. Well, when I think of sprawl, the one that comes to mind for me is the Cerebrus wafer scale engine, which is more like a dinner plate, right?
Yes, a dinner plate. Yeah, that is
Yeah.
the coolest technology. I can't believe how much fun those guys are having doing that. Now, they had to solve a lot of hard problems to make that happen, because these big wafers are very brittle and they could crack. They're not really designed to be used that way. They're designed to be cut up into pieces. So that's A, they had to solve. B, when you are using the system, they don't heat up uniformly. So some parts are going to heat up like really rapidly, the other side aren't, and that temperature difference can cause physical damage to the system. C, how do you qualify a chip? If some parts of it is bad, you have to be able to flaw it out and still use it. So you need some redundancy in how you manufacture things, such that one bad transistor isn't going to kind of ruin the whole thing. And then finally, you have to put it in a system and connect to it. Also, traditional chip equipment is expecting that you're going to have squares of chips on the die and then you're going to cut it all up. They're not counting on connecting those chips together on the same die. So they had to build technology that would allow you to actually connect those disparate chips on the same wafer together. And that's just the few that I can think of. I'm sure there are tens of other problems they had to solve that are simultaneously really challenging, but boy, they have to be really fun. So I envy those guys.
Well, and it's interesting though, with more and more capabilities on these mega chips, that ups the game. The OEMs, the systems makers, really have to up their game, don't they?
Well, yes, I think that's one reason why you see these chip vendors actually build and sell their own systems, is to show the way to the OEMs.
Right, like the Cerebrus CS2
Let's
system.
see, absolutely, that's right.
Yeah.
Samba Nova has their system. I mean, several others have their own systems. Sometimes they have it just as a reference architecture, like this is how you would do it, and then they would get an OEM to design it in.
Hmm.
Sometimes you build it and sell it and prime the pump, so to say, for a bigger company to come in with a bigger volume.
It's almost as though they're putting out a marketing prototype for the rest of the industry to see, try it out, and maybe lure in an OEM.
Very, very much. I mean, it's a good thing to do anyway, because you kind of solve the problems of how you actually use it in a system, and you work out some of the kinks for the OEM. But in the process, you also show the way, you prime the pump, you get the software going, you turn it into a more ready system to be used and make it easier for the bigger OEM to come in.
Okay, great stuff, Shaheen. Great to be with you again, and look forward to our next time.
Absolutely, looking forward to it. And of course, SC22 is coming, so we're going to do some previews of that as well in the coming weeks.
Looking forward to it. Thanks so much.
Take care. Bye-bye.
That's it for this episode of the At HPC podcast. Every episode is featured on InsideHPC.com and posted on OrionX.net. Use the comment section or tweet us with any questions or to propose topics of discussion. If you like the show, rate and review it on Apple Podcasts or wherever you listen. The At HPC podcast is a production of OrionX in association with Inside HPC. Thank you for listening.